아니, 아니 네가 이렇게 돼 있잖아. 근데 웹페이지 문자열은 A, B, C, D, F, 1, 2, 3, 4까지만 몇 개.
그럼 필요 없이 이게 더 빨라요.
Where I have been invest on 2%. I only using 1 year. Oldest, I think 26.
He's an independent network security researcher from Secure Bits.
All right. Can you hear me all? Thank you very much for being here. I'm Eyar Samhouri. I work for CCIC and company in Greece. I'm also an independent security researcher. I've developed some security researches and projects. They are available on my website, www.securebits.org. I also have a security blog, which is www.securebits.org/blog. The title of this talk is Next Generation Reverse Shell. The agenda of this presentation, I'm going to start by giving introduction to reverse shell, introduction to modern security architecture, and the attacker challenges, and how we can look at the modern security architecture to develop next generation reverse shell that could stand in advanced penetration testing in modern networks. Then I'm going to speak about the theory of next generation reverse shell and the technical implementation of it, and the HTTP-based, FTP-based, POP3, SMTP-based, and NTP-based implementation of this technique. And then I'm going to introduce the Giant Reverse tool, which is the platform for next generation reverse shell. And I'm going to close by giving a little bit about the future enhancement of the tool and conclusion. Now, look at this. This appears as timestamp. In fact, it's NTP timestamp in hex code. It looks like this. However, the ASCII representation of this hex is ls-l, which is a shell command. So I'm going to also introduce something called shell over NTP, which is part of the next generation reverse shell. So let's start. What is reverse shell? Well, a normal shell or a normal remote shell, the client or the user connects to the server, accesses the server, and then gains a remote shell over that system. Now, there is something I want you to note here. When I mention the word the user, I mean the attacker, the hacker, the security professional, the pen tester, or just a normal hobbyist, or anyone else. So when I mention the user, I mean anyone who uses the reverse shell or next generation reverse shell. So in normal shell, the user connects to the server and issues the command to the server to be executed. However, in reverse shell, the client establishes the connection to the server, and the user is working on the server and issues the command back to the client to be executed. So the direction of the execution is on the opposite direction of session establishment. That's the difference between reverse shell and normal remote shell. Now, reverse shell is used to access systems behind firewalls. Now, when you establish a connection to a system in an internal networks that's behind a firewall, the firewall is going to block you if the firewall blocks all inbound connection. However, if the client connects to the outside, to the server, to you, and then you issue the command back to the server, you can have remote shell, which is in reverse established connection. So the purpose of reverse shell is to access compromised systems or normal systems that are behind firewalls. Now, that's the basic idea of reverse shell. There are some implementations, some tools that you can have a basic reverse shell. I'm going to cover these basic implementations. And then I'm going to address the limitations and weaknesses of this implementation, the current implementation of reverse shell, so we can understand the need of next generation reverse shell. Reverse shell, normal reverse shell can be established using Netcat, which is a famous network security tool. Netcat can work in a client and server modes. You can see in the slide, you can execute the following command on the server, which is the server controlled by the user, and then you run the second command on the client, which is the system behind the firewall. And then Netcat is going to establish connection back to the server, and at the same time, it will attach the shell process /bin/sh to the TCP stream, and you are going to have reverse shell to the client. Reverse shell can also be implemented using SSH. Using SSH, of course, is going to be completely encrypted. Now, on the client, which is the remote machine, you issue the first command, which actually tells the SSH server on the client machine to connect to the remote machine or the server IP, the remote server. And then once it connects to the remote server on SSH, it's going to listen on port 1234. And then the user who's actually gaining this reverse shell will go to the server and issue the second command, and he will connect to his PC, which is listening on port 1234, which was already established by the client. So you're going to have reverse shell over SSH. Here is a very small script, for example. Let's say the compromised system. You have compromised a system, and that system doesn't have SSH or Netcat. Here is a small script, a super script developed by Julius Blends, and it initiates a connection back to the server, takes the command from the server, executes it on the client machine. This has a problem, though, which is it does not preserve the current working directory, which means once you have this shell, it doesn't provide you with interactive shell. You cannot issue command like cd or change working directory and so on. Another tool developed by Van Houser from the Hacker Choice, it's called reverse www shell. It's actually a little bit better than the previous implementations, though it has its own weaknesses. It's a proof of concept of his paper he has written. This tool provides reverse shell over HTTP protocol, tunneled within HTTP protocol. It works in master-slave mode. You have the slave on the client and the master on the server, and you have reverse shell over HTTP protocol. Now, looking at these implementations, we find the following. First of all, some implementations, they don't provide you with interactive shell. Others do, but some don't. Now, all of them provides you with only one shell over the established TCP stream, which means the following. Once you have established the reverse shell tunnel, you can only have one shell process running on the client. You cannot open other shells at the same time, running at the same time over the same TCP stream. If you want to have multiple shells, you need to execute the command again and again, 3 times, 4 times, to have the number of shells you want. That's another weakness. All of them, they don't provide means of mutability. For example, you establish the connection from the client to the server, and suddenly you want to change the server to a different IP address. You want to change the IP address. In this case, you have to rerun the program again on the client so that it connects to the new IP address. We cannot have a dynamic way of changing the server IP address on the fly. Now, if you are talking about advanced penetration test, we need a tool that provides us with dynamic way of changing the server address or port number on the fly. Another weakness we can see is every server can control one client at a time. You cannot control multiple clients at the same time. If you want to control multiple clients, you have to run the server multiple times at the same time, and every server is connected to one client. Again, in advanced penetration test, this is not very advanced. So, here comes the idea of next generation reverse shell, which provides maintainability, reliability, flexibility, which I'm going to discuss later on. Now, in order to see the need for these characteristics, let's review the modern network security architecture we found nowadays in modern networks. Mostly nowadays in most corporate networks, there are components, security components that are found in every networks. In even small corporate networks, they have these components. Whereas in the past, it wasn't like widely available. Every corporate network now, they have network level firewall, application level firewall, or protocol inspection scanning, IDS, IPS, DMZ, authentication proxy, and so on. These are very critical. And we are going to see why soon. Network level firewall, they just deny or allow traffic based on the source IP, port IP, source IP, destination port, and source port. Now, in the past, administrators used to place restrictions only on the inbound traffic, which is traffic coming from external, while outbound traffic, there was no restriction on that side. Now, nowadays, restrictions are placed on both directions. And this is very important because in the past, when you exploit a system, it was very easy to initiate, for example, a connection on high port number. Nowadays, you cannot do it. The protocol inspection engine monitors protocols for standard implementation, which means if port 21 is open, it's not enough to send any traffic on port 21 because the protocol inspection engine is going to make sure that the traffic is exactly FTP standard protocol, otherwise it's going to block. So if you find specific port open in the firewall, you cannot send your attack within that port if your attack does not comply with the standard implementation of the protocol. This applies to protocol like SMTP, POP3, FTP, DNS, ICMP, NTP, etc. If you want to use a port, the traffic has to comply with the standard implementation. IDS, IPS, they also monitor traffic against non-signatures, and the signatures are updated. Even if your traffic comply with the standard implementation, if they carry non-signature, for example, there is a user field which is a field you can manipulate. If that field contains, for example, a shell code, and this shell code is not sophisticated enough, it's going to be detected by the IPS and IDS. Now, DMZ. DMZ nowadays is part of every network. The interesting feature of DMZ is not the security of the DMZ itself, it's how administrators sometimes overlook important issues with the DMZ. A critical server that's in the DMZ could be allowed to have outbound access to the internet, unlike the servers which are on the inside. For example, as I said, the restrictions are placed on the outside interface and the inside interface of the firewall. Now, for DMZ, sometimes there is no restriction on the outbound traffic. There is no restriction on the ICMP traffic. So DMZ servers can ping outside, can send NTP protocols, etc., whereas internal servers cannot. This is very important for us because if you compromise a server in the DMZ, you can utilize protocol like ICMP or NTP to tunnel your own reverse shell. Authentication proxy is very important nowadays. People cannot browse the internet without proxy, and the proxy makes sure that the users are authorized through their account credentials and so on. So if you compromise a client, and that client cannot go to the internet except through a proxy, you have to make sure that you have the hashes, the authentication credential you can send with the attack, so you can tunnel your attack back to the server, to the outside. So this diagram summarizes the modern network security architecture, the 5 components I just spoke about. You can see the network level firewall behind the inspection engine and the IPS or IDS. You can see the DMZ segment, which is isolated from both the internal and external network. You can see the authentication proxy, which is between all the users, all the clients within the corporate networks and the outside world. Now, let's look at the attacker challenges. How we can view this from attacker's point of view. When we want to develop a world-class tool or world-class methodology for penetration test, we need 3 factors to keep in mind. The first factor, we cannot rely anymore on inbound connections or arbitrary outbound connections. That was in the past. Nowadays, inbound connections are blocked except the needed traffic. Arbitrary outbound connections are also blocked. High ports are blocked. Only the needed outbound traffic or connections can be made. When you want to tunnel your attack, or when you want to tunnel a shell, your traffic has to comply with the standard implementation of the protocols that are allowed through the firewall. Otherwise, inspection engines are going to drop your connection. The last thing, one of the most important aspects of compromising a system is not the exploitation itself. It is to have a persistent access after you exploit the system, which means if you exploit a system and then you have access for a few seconds or a few minutes or hours, and then if there's a firewall reboot by the administrator, you lose your connection and you no longer have access to the compromised system, that's not very advanced. And that cannot stand in advanced penetration test. So we need a way, when we compromise a system, to have persistent access. We can access it now and then come back tomorrow and after tomorrow, even if there is disconnection in the traffic, even if there are patches installed and so on, you can still maintain that persistent access. So these are the three challenges we need to look at, and the technique of next generation reverse shell addresses these challenges. So let's look at the theory behind next generation reverse shell. Next generation reverse shell provides 5 main characteristics that are not available in basic reverse shell. These characteristics are reliability, maintainability, flexibility, stealthiness, and inspection evasion. Reliability. Once the reverse shell is established, reliability guarantees you to have a continuous access in case of disconnection. For example, if you have a reverse shell connection and then the server reboots or the firewall reboots, there is an auto re-establishment of the connection. There is also keep alive messages that are sent frequently between the client and the server to maintain the session. And these keep alive messages detect any changes, any disconnection, any changes in the server IP, any changes in the server port numbers, and so on. So it's completely automatic. It detects all the disconnections, all the changes automatic, and it readjusts itself automatically. Maintainability. Let's say you establish a reverse shell to a compromised system that are behind a firewall and internal network. And then you want to change the server IP. Maintainability means to provide you with a dynamic way to change the IP address without rerunning the program again on the client. So while having the reverse shell connection, you can change the IP address. You can instruct the client to change the IP address and connect to another IP addresses directly. It will just stop your connection, establish the connection with the other server, and you have reverse shell on the other server. Or, for example, you are having a reverse shell tunnel, let's say in HTTP, and then suddenly you want to change it to SMTP or POP3 tunnel. You cannot rerun the program again on the client. All you have to do is to issue a command from the server to the client to re-establish the connection on the desired ports. These are the means of maintainability. Flexibility. I said before that the current basic implementation of reverse shell, they only provide you with one shell process per connection. You cannot have multiple shells. Now, with the next generation reverse shell, you can have multiple shells over the same stream. When you establish the reverse shell session between the client and the server, you have one shell. Let's say you want to create another shell. You can issue a command, and then you have another shell. Both shells can be accessible through the same TCP stream. You don't have another TCP stream. It is the same single TCP stream, and I'm going to show you a demo for that. It is the same TCP stream. You are accessing 2 shells or 3 or 4 or more. And every shell preserves its own current work directory as well. For example, you can have the first shell working in slash directory, the other shell working under slash boot, and so on. The other feature of flexibility is that you can control multiple clients at the same time. From the single server, it's always listening on more and more connections. Once you have connection from a compromised client to the server, and you are having a reverse shell to that client, you can also wait for another connection from a different client. So you can have one server controlling multiple clients at the same time, and you can switch on the fly between those clients and change your control. You control the client, and then you work on the other client. Stealthiness. Next generation reverse shell provides an option of encoding. You can encode the shell transaction while being tunneled in the standard protocols. This is very important. For example, if you have command like car/etc/password and you are trying to dump the password file, you don't want that to be visible in any network sniffer. So encoding provides a good mean of stealthiness. Inspection evasion. All the transaction of reverse shell that's taking place between the client and the server take place within standard protocols. Currently, the protocols implemented are HTTP, POP3, SMTP, and NTP. And in the future, we're going to have ICMP and DNS as well. So when you have a standard protocol traffic, your inspection engine the inspection engine on the client will not drop your connection because it appears completely standard. If it's FTP, you are tunneling within FTP, there's initial FTP transaction takes place before the reverse shell. So the inspection engine always sees standard traffic between you and the client. Now, let's move to the general technical implementation of next generation reverse shell. There are 5 points here that I want to discuss. Session establishment, executing shell commands, controlling multiple commands, the internal NGRS command system, and multiple shell spawning. Session establishment. Now, given that the protocols that tunnel reverse shell between the client and the server can be TCP protocols like SMTP, POP3, or HTTP, and UDP protocols, for example, like NTP, as I'm going to show you, the way session establishment differ between TCP protocols and UDP protocol. With TCP protocol, you know that the session is established when TCP three-way handshake takes place. However, with UDP, we need additional factor. And with UDP protocol, we implement a customized initialization and acknowledgement packets that take place at the beginning of the transaction between the client and the server, so we can know that the session is established. After the session is established, whether in the TCP way or UDP way between the client and the server, the client keeps sending keep alive message, and the keep alive message are pre-configured way on the client to send those packets to the server, and the server understands that these are keep alive packets. Keep alive packets have two purposes. The first one, they maintain the session between the client and the server. So for example, if the user stops typing commands on the client, on his server that sends it to the client, now, for example, for a couple of minutes or more, the inspection engine on the client network is going to drop the connection because it sees that the timeout has expired. However, with keep alive messages, the connection is always alive. The second purpose of keep alive message is that any command you send from the server to the client is carried in a packet that's a reply to the keep alive message. For example, if you are tunneling in, for example, FTP, the keep alive message would be something like FTP request. And the command that you send from the server to the client will be coming as a reply to that message. So the keep alive message is used as well as a request for which the reply carries the command from the user to the client. This diagram shows the session establishment and the difference between TCP and UDP. In the TCP section, TCP three-way handshake takes place, and then keep alive messages are sent at periodic basis. However, with the UDP, there is customized initialization and acknowledgement packets that take place between the client and the server, and then keep alive messages are sent at periodic basis as well. Now, let's talk about how commands are being executed on the client. You see in the first example I show you, which is the netcat example, netcat does the following. It attaches the shell process to the TCP stream. So the shell is attached to the TCP stream, and the standard input and standard output of the shell is actually the input and output of the socket, of the network socket itself. However, the way we implement it here with next generation reverse shell is we have the shell process running separately on the client. It's actually forked on the client, and then it pipes its standard input and output to the main process. Now, this enables us to check every command coming from the server or the user to the client. So the client process, the main process, can check this command before it passes the command to the shell process to be executed. Not only that, the other advantage of having a separate process for shell is that we can fork multiple shells at the same time. We can fork multiple processes, and every process has its own shell. So we can have multiple shells at the same time. Something else. When we issue the command from the server to the client checks it if it is an internal command. I'm going to discuss internal command shortly, but before passing any command to the shell process to be executed, we check if this command is internal command, which is different than shell command, so that we can control the behavior of the reverse shell tunnel itself. Okay. Here's the diagram. You can see the main process, it forks a shell process, and then the shell process is piped to the main process, and any command coming to the main process can be diverted to the fork process. And then the result is read back from the fork process. Controlling multiple clients. This is the third implementation feature. Controlling multiple clients happen when the server is listening continuously on the available ports. For example, if our server can tunnel reverse shell within HTTP, SMTP, POP3, the server is always listening on those ports, and then any new client connects to the server is going to inform the user of this new client, and the user can access that client and issue shell commands and have interactive shell. At the same time, while the user is having interactive shell with the client, the server is still listening for more clients, so that you can have multiple clients being controlled at the same time. Now, coming to the internal and GRS commands. In order to maintain these features of flexibility and reliability, etc., we need to have a system of internal commands. For example, you are trying to control a client and you are issuing shell commands. At the same time, where you issue the shell commands, you can issue specific commands called internal NGRS commands, and these commands are not passed to the shell process to be executed. They are checked by the parent process, and then every command has its own behavior or its own performance. So the client performs specific action when it receives one of these commands. Currently, there are 16 internal commands. I'm going to go through them quickly. Set server IP and get server IP. You can change the server IP address or get the current server IP address at the same. You issue this command like issuing any other shell command at the same place. For example, you issue, for example, ls. At the same place, you can issue, for example, set server IP. You give it another IP, and then you have another connection from the client to that IP. Set the protocol and get the protocol. You can set the tunneling protocol on the fly using this command. For example, if you have the tunneling protocol HTTP, you issue set protocol FTP, and then you have an FTP. Get protocol, you get the current tunneling protocol. Set port and get port also change the port number of the tunneling protocol, of the tunneling traffic. Set encoding, get encoding, you can set or switch on, switch off encoding. Create shell, delete shell. You can create multiple shells. For example, when you establish the reverse shell connection at the first time, you have only one shell. With the create shell command, you can create another shell. You issue create shell again, you have a third shell, and so on. And the command set shell can actually switch between the interactive shells. For example, you have now shell number 2, you are accessing shell number 2. With set shell, for example, you can say set shell number 4, and then you are accessing shell number 4, executing command shell number 4. The final command, sleep command, you can, for example, if you are controlling client right now, for example, and then you want to go, for example, for 10 hours and then come back and have your shell, you can just type sleep 10 hours, and then all the traffic is disconnected, no communication between the client and server, and after 10 hours, the connection is reestablished again. Multiple shell spawning, which is another technical feature here. You can see there are multiple shells running simultaneously at the same time. Sorry. Running at the same time, every shell preserves its own current working directory. You can see shell number 1, for example, in the third point. Shell number 1, it maintains the root directory. Shell number 2 /root directory. Shell number 3 /home, etc. So, for example, you go to shell number 3, you issue a command, it goes directly to that directory. You go to shell number 2, you are already on the current working directory of shell number 2, and so on. That's the advantage of having multiple shells at the same time. I'm going to delay the demo at the end so we can. Okay. Now I'm going to speak about the implementation, the technical implementation of every tunneling protocol. We have HTTP, POP3, SMTP, FTP, and NTP. With the HTTP implementation, we utilize the get and post methods. So, for example, every request or every message coming from the client to the server, they use either get or post. Get is used for keep alive message, while post is used to send the result back to the server. Now, how do you send the actual commands from the server to the client? You use them using the server, the HTTP response codes, which are 200 OK and 404 not found. So the client sent get request, and then the server issues 200 OK with the command, and then the client issues post with the result of the command execution. Here you can see this diagram. First, the client said, get I am ready packet, which is actually keep alive, and then the server responds to this message by sending 200 OK reply with the command enclosed with HTML to give it web taste, and then the results will be posted back using post method to the server. Okay, now we can see a quick demo here. All right. Sorry. Okay. Okay. We are going to see a reverse shell tunneled in HTTP protocol. So this server is actually the server controlled by the user, and that's the client, which is a compromised system behind a firewall. Now, okay. If I issue command get protocol, which is internal command, the tunnel is HTTP. Shell command, another shell command, third shell command, and so on. You see, we are having now reverse shell over HTTP. If you go to the sniffer here, I'm not going to go through all the packets, but you can see it's actually HTTP. All the traffic happens through HTTP protocol as get and post and reply and so on. Okay. Now we move to the FTP-based implementation. There is a difference between FTP implementation and HTTP implementation. To have a standard FTP traffic, we need to send, or a transaction, which is called initial transaction between the client and server, has to happen. And this transaction utilizes the command user pass, print working directory, and so on, and passive mode. There is something I would like to mention here, that in FTP implementation, we have the data channel and the control channel. The data channel always happens using the passive mode, because you need the client to connect back to the server, not the active mode. After the initial transaction happens, the client sends the FTP command called list, which actually instructs the server to list files on that directory. The server replies with file list, and the file list includes the commands from the user. So the commands, the shell commands issued by the user are transferred as file names to the client. The client extracts the commands, execute the commands, and get the results. The results are sent back as files. So the client issues the command, store the command name, and then on the data channel, it sends the command, the execution results. You can see here in this diagram, from all the server codes, 220, 331, and so on, these are the initial transaction between the client and server. This takes place only once at the beginning of session establishment. Later on, the list command is sent from the client to the server as keep alive message and as a request to the commands from the server. The server sends back the the results on the data channel, and then the server sent the command on the data channel, and then the results are sent back on the data channel from the client to the server. Okay, another quick demo here. On the server is listening, and then the client will establish a reverse shell tunneled in FTP protocol. Sorry. Now we have if we type get protocol, we see the tunnel is FTP. We issue a couple of commands. Sorry. Current protocol is FTP. We issue commands, and so on. And we can see on the sniffer that transaction took place over FTP protocol. At the beginning, there was the FTP initial transaction. These are the initial transaction. And then passive command was instructed, and then data channel was established, and all the transaction happened through the data channel. Okay. That's regarding the FTP. POP3 and SMTP implementation, similar to the previous one. However, POP3 is utilized to send the commands from the server to the client. So when you type a command, the command is sent to the client as a way of downloading an email. So the traffic, the communication between the client and the server happens, or it looks like as if the client is downloading an email from the server, while this email actually carries the commands. Now, when the client executes the command, and get the results are sent from the client to the server using the SMTP protocol, which appears as if the client is actually sending an email from the client to the server. Okay. The initial transaction takes place in POP3 and SMTP as well. I'm going to skip that. Okay. Demo is similar. Maybe I will show it after the NTP. The last implementation is the NTP-based implementation. Now, NTP can be used to tunnel data and can be used in our reverse shell technique, in next generation reverse shell technique. NTP header has a fixed size, which is 48 bytes. Now, we can use the timestamps field in the NTP header to tunnel our data. How we can do that? Since the header is fixed, has a fixed size, and we have a limited amount of bytes to send per packet, we can partition a chunk of data over multiple NTP packets and keep the sequence of the packets when we send those packets. So, we are going to use the peer clock precision field to carry the total number of packets needed to tunnel chunk of data, and then we will use the root delay field to carry the actual sequence of every packet. So for example, if you are sending 4 packets, you are going to have for the first packet 1/4, for the second 2/4, 3/4, and 4/4, until the last packet. And the 4 fields, the 4 timestamp fields will carry the data, and the reference ID will carry also a data. Here's an example. If we have 120 bytes of data, you can see it. Here's an example. 120 bytes of data can be transferred using 4 NTP packets. The first packet will look like something like this. We have the total number of packets, 4, and then the first packet carries number 1, and then the data is tunneled in the timestamps, and you can see the timestamps. They show actual timestamps. They show real times. The second packet will carry another portion of the data. The third one the same, and the fourth one. And with this, we have transferred all the data using NTP tunnel. We can use this technique to tunnel also our shell transaction, to tunnel the commands and the result between the client and server. So we can have interactive reverse shell over NTP. Okay, I'm going to show you one NTP demo and another multiple shells demo and changing protocols. So 3 demos and we close. So, get protocol, it's NTP, another command. We got the result, we go back here to the sniffer. We see all the transaction took place using NTP protocol. You can see here actually the data, they appear as if they are real timestamp. 1970, 2008, and so on. Okay. Last demo, which is multiple shells. Okay. I have one shell now. I can create additional shell. I have additional shell with ID 2. I can also create additional shell with create shell command, and I have a third shell. Now, in the first shell, I execute first command, and I change directory to the root directory, and then I switch to shell number 2 now, to shell 2, set shell 2. Now I'm in shell 2. I'm going to change the directory to something else. I issue another command, and then I change to shell 3. I'm in shell 3 now. I can type get info command, and now I have 3 shells. One has its own current working directory /root/ whatever. The second one /root, and the third one, which is the root directory. And you can see shell 1 has executed 0 command, shell 2 executed 2 commands, shell 3 executed 2 commands. So you have multiple shells running simultaneously. Every shell has its own current working directory. Okay. Now, the tool that implements this is called Giant Reverse, GR. It works in client mode, in client server mode. The same application you can run it both on the client and the server. It is the client and the server, and currently it implements the 4 protocols: POP3, SMTP, FTP, HTTP, and 5 protocols and NTP. Future work may include adding other tunneling protocol, ICMP and DNS. Also, future work, we are going to add remote desktop connection over reverse tunneling protocol and VNC over reverse tunneling protocol as well. So instead of having only reverse shell, you can have reverse remote desktop connection over FTP, SMTP, POP3. The same way with the reverse shell, but we can have it with remote desktop connection, a graphical interface, etc. So next generation reverse shell provides reliability, flexibility, maintainability, persistent access to compromised system. You can control multiple clients. It has different tunneling protocols. And that's it. Thank you very much for listening. If you have any question, I'll be more than happy. Any question? Download? You want to download, you mean? Yeah. The presentation, there is a white paper on this, and the tool available on my on my website, securebase.org. You can find the presentation, the white paper, and the tool as well. The current tool is in beta version. Soon it's going to be the first release. So you can have it all on my website.
Excuse me. You mentioned about the keep alive message.
Yeah.
Through our UDP.
Mm-hmm.
So supposedly it generates the traffic, right?
Mm-hmm.
So basically it's using what ports?
Sorry, using?
What port? Which ports?
Which port depends?
Yeah,
on
for the
protocol.
UDP, for the keep
example,
alive message.
If you are using NTP protocol, the UDP port will be 1, 2, 3.
Okay, so is it possible that you can do things like, for example, you use the keep alive message particularly for like, if you're using for HTTP, you use the get post as a keep alive.
Exactly.
Yeah.
You send get request as a keep alive, yeah.
Okay, so for the keep alive, I mean, if you still use UDP or you still use back port 80?
For keep alive. For
keep alive message.
HTTP, you mean?
Yeah.
You send the get request over TCP, normally on port 80, yes.
Oh, okay, so for the HTTP one,
Every protocol has its, every tunneling protocol has its own port number, its own way of implementing the keep alive message. So HTTP keep alive message is different than NTP keep alive message. It's different than the FTP keep alive message.
Yeah.
And POP3 keep alive, yeah.
okay,
And so on.
okay, so basically it's try to avoid the detection, right?
Sorry?
I mean, it's trying to avoid the detection of it. The detection of a certain tunneling stuff.
Again, what do you mean avoiding detection?
Because let's say if you are using a different kind of parts to do the keep alive, so basically people can identify it. So if you are using a same protocols like HTTP, you use get and post to do keep alive, so people basically won't actually look at it.
Well, for every tunneling protocol, you specify the port number, and the port number can be changed dynamically. You can change the port number, yes. But every keep alive, when it is sent according to the configured protocol, using the configured protocol on the configured port number. You can change it, yes. But once you have it, for example, HTTP tunnel, you cannot have keep alive in FTP. It's always in an HTTP.